Hello, everybody. Sorry for the couple-minute delay. Hopefully, enough people got my message to get started on the question that was right in front of you. Yeah, so yesterday didn't go that badly, did it? Nobody wants to talk about it? Fine. Unless nobody can hear me at all. Yeah, I expected the world to explode. Nothing exploded. At least, not mathematically, anyway. Whether things exploded mathematically might be a different thing, but that's a matter of opinion. Alrighty. So I had like 3 computers going in terms of what happens if something crashed. No. So things seem to have gone well. I've already had some people asking about a couple things in regards to the midterm, so I will address them. If you don't want to hear them, there's a question on the screen. Feel free to start with that. The first thing about it is it won't be a quick process to get these things marked. It's not like the term tests where they're being taken at different times and markers can be marking throughout when the tests are being done. Everything's done at once, so it takes a bit more time. My best estimation is late next week. But I'm not going to make that a guarantee, just an estimation as to when the midterm will be back to you. And sometime over reading week, we'll have a discussion amongst the professors as to what is on test 4. That's quite premature. But technically, there's only 1 week worth of material until then because reading week just sucks that out. So if you are curious about test 4, which wouldn't start until the Friday after reading week, that'll come out as well. The deferral for people who were sick or something, make sure you get in contact with me by the end of tomorrow. And that'll be an actual, unlike the term tests where things aren't, there's no makeup test. There is for the deferral. I don't have an exact date yet. I'm working with the people who make decisions, some of which are here, some of whom are not, to get a date set. My best estimation will be early after reading week. That is certainly my hope, for a variety of reasons. That is my hope to get the deferral done as soon after reading week as possible, but I don't get to just make these decisions on my own. So anyone who did miss the test, you should have already been in contact with me. If you were ill or otherwise had a good reason not to be there. If you didn't, make sure you get in touch with me sooner rather than later. That way, when I have an exact date, I can send it out to everybody who is affected. And I've had a few people, at least 3 or 4 people, emailing me with concerns about the last questions, part C and D, saying it had material from sections 3.2 because they claimed the dot product was necessary to solve it. That wasn't true. You did not need, it's not wrong to use it, but you did not need the dot product to answer parts C and D. You needed nothing but scalar multiples. So if you were concerned or thought something was unfair, you can think things are unfair for a variety of reasons. I mean, that is what it is. But material from 3.2 was not needed to answer the last 2 parts of question 6. Scalar multiples was all that was needed, and that was done in 3.1. So that being said, if you use stuff from 3.2, that's not wrong either. So it's not like if you didn't do it the scalar multiple way, that somehow you're going to lose marks for that. That's not a problem either. Can the midterm get curved up? We don't curve individual assessments in this course. We will take a look at the final grades at the end of the term and then decide whether any adjustments need to be made. So we don't make any type of curving or decisions based on any single assessment. We look at the class as a whole. Because just like one test might be a super low average, one test might be a super high average, and they could even out over time. So we just don't make those decisions until the term is done. All right, if anyone has any other questions regarding the midterm, feel free to keep firing them off. If not, like I said, there's a question in front of you. Feel free to get started. I would have no idea. I haven't been involved in this course for 5 years, so I wouldn't have the data on anything from any recent term. If it was a non-pandemic term, I could make a reasonable guess. With it being pandemic, I know the pandemic. The course I typically teach is Math 1500, Calculus 1. I've taught that every term for the last 5 years. So I know how that course was affected by the pandemic, and it was enough for me to think that any guess I would make from 1300 based on previous knowledge is probably not applicable to any recent term. So, but if it's like my calculus class, not high. The pandemic messed around with the average. Overall, the people who didn't drop tended to be higher, but a lot more people just got really awful grades. So if anything, I found in Calculus 1, the pandemic increased the spread. Like a lot more, lower grades, but the ones that stuck around got higher grades. Granted, in Math 1500, we ran weekly tests instead of a midterm just because they have longer tutorials, so I could take up test time in every single tutorial. So the structure was also different, so it's really hard for me to make comparisons. I would have done it in this class as well, but we only had 50-minute tutorials, in which case if I did that, pretty much all the tutorial time would be wrapped up in tests, and I didn't want to do that. I shouldn't just say I. It's not like I make these decisions on my own, but alrighty. Anyway, so in this, honestly, this question, tell me about it. In this question, we're talking about the equation of a plane given a normal vector and passing through a point. So the second part of this question is almost identical to how we did the last example on Tuesday. But here we want to actually find the equation of a plane. So in fact, if you know what you're doing, the answer to this should be really quick. So what is the equation of this plane passing through the normal vector 1, -4, 5, and p 1, 2, 3? So what's the equation of that plane? Curious where you're getting root 14 from. Where do we get root 14 from? Okay, that wouldn't be part of the equation. That wouldn't be part of the equation because there's no guarantee that we're passing through the origin. But the first part of that was absolutely right. So a plane has the equation, or the standard or general form of the equation looks like ax plus by plus cz plus d is equal to 0, or the d could be to the other side. That one doesn't really matter. In this context, that doesn't really matter. And as we saw on Tuesday, what is A, B, and C? What's the relationship between A, B, and C and the information we're given? Yeah, we can use the normal vector there. It doesn't have to be the normal vector, but it can be. And so we get x plus b, which is -4, y plus c, which is 5z, but what we don't know is the number, regardless of which side that it's on. All right, so the coefficients of x, y, and z, that's going to be our normal vector. The question is, how do we solve for the d? How do we solve for that d such that not only is it this normal, but it passes through this point? And as mentioned there, that absolutely we're going to plug in our point. So we plug in 1, 2, 3, and we get 1 minus 4 times 2 plus 5 times 3 plus d is equal to 0, and then we just solve for d. So 1 minus 8 is negative 7, plus 15 is 8, plus d equals 0. So d is equal to negative 8. And hence we get x minus 4y plus 5z minus 8. Or if you prefer, you can move the 8 to the other side. Either way, we get a perfectly acceptable equation of a plane. All right. So, any questions about how we got our equation of that plane? All right, so back to the question, the distance question. So we have this point P that we know is in the plane. I've drawn it like it's horizontal, even though it's not, but the ideas will still work. Q is the given point. I don't even remember what it was offhand. I think 2, 3, 4. And we want to find the distance from Q to the plane. So what distance are we talking about? Let's be clear what kind of distance we're looking for. Right, we want that shortest distance, which means the so a perpendicular distance, which is fairly unlikely to take us right to P. So this is the distance we're looking for, very similar to the line example we finished off with on Tuesday, for those that were still paying attention on Tuesday and not thinking too much about the midterm, and now all of a sudden have realized, oh right, there was a class on Tuesday. All right, so how do we find that? How do we find this distance? How do we find that distance? Pythagoras could be interesting. Unfortunately, to use Pythagoras, we'd have to make this right triangle, which is fine. And yes, we know this. And we want to find this. But we don't know this bottom part of the triangle. If we knew that, then we could use Pythagoras. But unfortunately, we need to know two sides to get the third, and we only know one side without a lot more work. So Pythagoras doesn't really help us, not directly, although you could indirectly work with it. But yeah, how do we know the great question. How do we know the hypotenuse? I mean, technically it's not relevant to this question, but how do we know the hypotenuse? Yeah, it's the length of PQ. We have P, we have Q, we can find PQ, and it's the length. Again, we're not going to, but we could find the hypotenuse, but we don't know the other two sides. Some people are saying the projection, so let's be very specific. The projection of which vector onto which other vector? It is a projection, but which vector onto which other vector? Yeah, so PQ onto something, that's half of it. Yeah, we're going to do the projection onto the normal vector. Now, again, we don't know the length of the normal vector. The normal vector could be a lot longer. The normal vector could just be this. The normal vector could go in the opposite direction. In theory, in this case, we could make a more reasonable assumption. But the idea is we only know the direction of the normal vector. Fortunately, the projection takes that completely into account. That's what the projection's all about. And so we can find our projection of PQ, or if you want, you can use QP, either one is fine, onto our normal vector. And then it just turns into our formula for the projection over the length of n squared times n. And now it just becomes another projection calculation with a distance thrown in at the end. All right, so any questions about the geometric ideas behind this? All right, so 1, -4, 5. PQ is 1, 1, 1. We know how to find PQ. Subtracting the components, we get PQ is 1, 1, 1 over the length of n. So that's 1 squared plus -4 squared plus 5 squared times n, which is 1, -4, and 5. Why did we project PQ onto n? It's because n is this direction, and we just want the part of it that is contained within PQ, and that's exactly what a projection is what part of the vector, in this case, the vector being the normal vector, what part of that is projected onto from PQ. And because PQ kind of just goes here, the projection would give us this vector right there. And that's just completely what a projection does. Yeah, I didn't actually square it yet. Perfect, thank you. It would be the length squared, so the square root does go away. That numerator is going to be 1 minus 4 plus 5 is 2. Squaring stuff out in the denominator, that's what, 42. And then 1, 4, and 5 for our length. And so we get, what is that? 1 over 21 times, once again, the exact same length calculation, which means you could probably do some canceling there. And we get the square root of 42 over 21. So any questions about how we computed that projection? Just a reminder for anyone who so this was the whole projection stuff. So if we want to project U onto A, we find U, we drop this perpendicular, and then the projection is just the piece in that direction. That's what the projection is. And so that's exactly what we're finding in this question here. Although technically we're finding the length of said projection, not the projection itself, but the geometric ideas are the same. All right, so any questions about this or any of this distance stuff? Or anything from 3.3 for that matter? All right, bang. So that brings us to section 3.4, and we kind of already did a little bit of this, where we talked about the equations of lines and planes. So I'm going to answer a couple more questions that came in the chat, but for those that hopefully viewed the pre-lecture videos, see if we can give this question here a try, where we find the equation of the line passing through a given point and parallel to a given vector. Do we have to subtract the vector u from the projection? Depends on what we're projecting onto. So this might actually be easier for me to explain from the last example we did before. It's a little harder with the plane, although I'll try. If we go back to the example we did finish Tuesday with, had we so in this case here, we found the projection of QP onto the n. So it depends on what we're looking to find. someone suggested on Tuesday, or maybe it was my other class when I did the same example, my memory's not great, is that we could have projected onto this vector right here. Had we projected onto this vector, then we would have gotten this, and then yes, we would have subtracted to get that. So it depends on which one we're projecting onto. So since we're projecting to the perpendicular already, subtracting isn't necessary. Had we projected onto the not perpendicular part, then we would have gotten, had to do the subtraction thing and find that orthogonal complement. So in this case, here's the n. So that's n. And this was just the line, and we didn't actually find a vector parallel to that. So we didn't actually even bother doing it because we didn't need it. It's even more confusing when you start to think about a plane, because we really just don't know. I mean, we could, in theory, find it, but we really just don't know what that vector is. Like, we just don't know it. In which case, the subtraction even makes less sense in that context. Not really. We're dropping P onto the point where N and the plane intersect. Not sure I quite understand the question. Like, we're talking about this point here. Yeah, so we're I guess in one way you could think of that, sure. We're finding, if we think of this as, maybe the sun is coming from the side, we're trying to figure out its shadow. Then we're finding QP, and then we're kind of just projecting it down here to get what this vector would be. I mean, we'll technically never find this actual point, nor do we actually need the actual point. But yeah, it's effectively what any projection is doing. It's taking it down onto the original vector and then finding that new either vector or length, depending on the context. All right. So this question here, we want to find the equation of a line. What do we need to find the equation of a line? Again, I'll try and be a little bit more explainy because some of you may or may not have viewed the pre-lecture videos in terms of the fact there was a midterm last night. I appreciate the ones that did. This will make more sense if you did. So if this was two-dimensional, what do we need in order to find the equation of a line? We need the slope, and we also need what? And we need a point. We need a point, we need a slope. Ideally, the slope, that point is the y-intercept, but we can figure it out even if it's not. So we need a point, we need the slope. Y equals mx plus b. Beautiful. All right, in 3 dimensions, there's a z, so that can't work. So we're going to do the next best thing. All right? Instead of finding the slope, we're going to do the next best thing. So here's the line we want, and we know P1, 2, 3 is on the line. And the idea is V is a vector that's parallel to this line. Now, what is an equation? Let's get meta here. What is the whole purpose of an equation of any geometric shape? What is the entire purpose? If I said the shape of this particular equation, technically that's a circle. It's not really relevant to what my point is. But if I give you an equation, how does that relate to the geometric shape? If we plug in values of it, if x and y satisfy this equation, what does that mean? Right. It's a point on whatever the shape is. If x and y doesn't satisfy that equation, what does that mean? It's not on the shape. Exactly. So whenever we're looking for an equation, and this is true for any equation that you've probably ever seen in terms of the equation of a parabola, the equation of a circle, the equation of a line, it's all about the geometry setting up a relationship such that xy or xyz, if it's three-dimensional, xyz, that if you're on the curve, in this case, if we're on the line, we satisfy the equation. If we're not on the line, we don't satisfy the equation. So in other words, we want to take some random thing, x, y, z, and we want to come up with a rule. A rule that says if x, y, z satisfies this rule, then it's on the line, and turn that rule into an equation. That's how effectively the equation of the parabola was formed. The equation of a circle is formed. It's all about, hey, we want to satisfy the rule of the shape, in this case a line, so that if we satisfy the equation, we're a point on the line. So what's the rule for Q to be on this line? What has to be true here? P is on the line is parallel to V. What has to be true? What's the geometry going on here? Before we get into an algebra statement, what's the geometry happening here? Yeah, PQ is parallel to V. Q and P are points, so they don't really... I mean, yeah, okay, you could turn them into vectors, but if you did, you'd need an origin, and I don't have an origin here. Well, PQ is going to be parallel to V. All right, so we have a geometric idea. If Q is any point on this line, then PQ is going to be parallel to V. Why what? Sorry. That's the question. Find the equation of the line which is parallel to the vector. That's what V is a vector parallel to the line. And that's important. I mean, that's a necessary part of this. All right, so we've got the geometric idea. Let's turn it into an algebraic statement. Algebraically speaking, what does it mean for PQ to be parallel to V? We got the geometry. Let's turn it into algebra. What does it mean for PQ? Now, same slope makes sense in 2 dimensions. Doesn't always make sense in 3. Right, it's a scalar multiple. So PQ is going to be some multiple of V. T is some real number. That's what it means to be a scale, to be parallel. If T is positive, it's going in the same direction. If T is negative, it's going in the opposite direction. But it's a scalar multiple. That's what it means to be parallel. Now we have an equation, and we can just go with it. we know that PQ is the same thing as Q minus P, so that would say XYZ is equal to 1, 2, 3 plus T times V, which is 3, negative 1, 2. So that's where this equation comes from. It's the fact that PQ is equal to a multiple of V. And we call this thing the vector equation of the line. But it comes from the fact that PQ, which is XYZ minus 1, 2, 3, yeah, we're just moving the P to the other side. So technically it starts with this minus is equal, and then we just move it to the other side. Which means we can find a bunch of different values, right? How can we find other points that are on this line? How can we find points on the line? Plug in values at t. Plug in t equals 0, we get the point 1, 2, 3. Plug in t equals 5, we get a different point. Plug in t equals 10, we get a different point. Plug in t equals e to the pi divided by root 17, we get a different point. Plugging in all the possible values of t gives us all the points on this line. So that's the vector equation of the line. There's also another way of writing it, which is the parametric equations of the line. What's the difference there? Hey, parameter. There's a word we're familiar with. What's the difference with our parametric equation? Yeah, so the difference between the parametric equation and the vector equation is we're going to treat each variable separately. X equals, Y equals, Z equals. Kind of like we did when we solved systems of equations. We had a way of dealing with the variables separately as part of our solution, but we could also combine them together into, we didn't call it a vector then, but it's effectively a vector. All right, so what would be x? If x, y, z is equal to this right-hand side, then if we just looked at the x components, what would we get? Yeah, 1 plus 3t. What about y? We looked at the y components. 2 minus t. And again, if we looked at the z components, three plus 2t. So they're both accomplishing the same thing. They're both perfectly valid equations of the line. Whether we write the components separately, the x, y, and z separately, that's parametric equations, and you'll notice this looks very similar to when we solve systems of equations in chapter 1, and we'll see that connection later. Or we can combine it into one in just a vector form, and that works just fine. Great. So any questions about this? The general idea of how to do this? All right then. Give this question here a try. Slightly different, but try and use the same ideas. So hopefully you had a chance to think about this. So given what we just talked about and our strategy that we saw in the last question, what are the two things we need in order to find the equation of a line in 3 dimensions? Because slope doesn't make sense anymore in 3 dimensions, at least not in the same way. So what two things do we need to find the equation of a line? We definitely need a point. What else do we need? All right, we need a point and we need a vector parallel to the line. That's what we're looking for. In the last question, we were given both right away, so we could jump right into our answer. I, educationed it up a little bit to explain where the equation came from, but to be perfectly honest, given a point, given a vector parallel, we should be able to jump right to our answer. In this case, not quite so much, because we're not given a vector parallel to this line. We're given twice of one thing and not enough of another. So, what can we do? How we're given a point, that's not the problem. How do we find a vector parallel to this line? Right. So, the vector we're looking for is just PQ itself. Again, if you think about it, here's a line, here's a point P, here's a point Q. PQ is parallel to that line. In fact, PQ is on the line. So we aren't explicitly given the vector parallel to the line, but since we have 2 points, we can subtract those points and we'll get a vector parallel to the line. So in this case here, 3, -2, -2, 1, -3. So we're not given it, but we can calculate that vector parallel to the line, and now we have enough information to be able to answer the question. Can we assume which vector is parallel? I mean, we're not really assuming it. If we have 2 points on the line, maybe you asked the question before I said that, but if we have 2 questions on the line, then it will be parallel for sure. All right, so again, in vector form, we get x, y, z. Now, which point do we have to use, P or Q? Which one would we use, P or Q? We need a point for the point part. The vector part, we definitely use PQ. But for the point part, yeah, both of them. Yeah, the answer is it doesn't matter. The answer is it doesn't matter. So I used P because I saw P first. If you really like this Q, if you like the number 4 and you want to use it, go right ahead. You could have used 4, -2, 1, which might seem weird because it looks like a different line. But it's not actually any different. And I'll talk about why in just a second. So this would be a perfectly fine final answer for the vector, for the parametric. X equals to 1 plus 3t again. Y is equal to 2 minus 4t. And Z is equal to 3 minus 2t. So the key is, if we ever want to find the equation of a line, we need to find 2 things: a point on the line, a vector parallel to the line. So any question about finding the equation of a line boils down to trying to find those 2 things. Any questions about how we found or how we did this example? All right, so what if we did use the other? Like, this looks different. Like, isn't this equation different than the other one? I mean, I'm claiming it's not, but that seems really weird because 1, 2, 3 and 4, -2, 1 are different. So why are these not different lines. Got an answer for that? Because they look different. Sure. I mean, the point determines where it starts. That's a fair enough assumption. I mean, a line doesn't really have a start and a finish, but right, but we're talking about a line, and a line doesn't have a direction. I mean, geometrically, it might make sense. I mean, here's P, here's Q, and we're just going off in different directions from different starting points. So if you'll want to think of it geometrically, we're just going off in the different directions from different starting points on the line. But algebraically speaking, these look different. Why aren't they different? For example, if I let t equals 2, we get a point. What point do we get? What point do we get if I let t equals 2? I mean, that's how we find points on the line. Plug in values of t. So what do we get for x, y, z? Yeah. So the point we get, I'll call it r, I guess, is 7, -6, and -1. So if these are the same line, then 7, -6, -1 had better be on this line too. If these are in fact the same line, then if the point 7, -6, -1 is on the first line, it sure as heck better be on the second one. So is this point 7, -6, -1, is that on the second line? Sort of. Yeah. If t is equal to 1, then there we go. So the point being is, if you use a different point, it might look different, but you will get the exact same points on both of these lines. You would just use different parameters to get it. And in fact, if you take a look at any point on this line for any value of t, take one bigger value of t and you would get it on the second line as well. So the point being is we get the exact same points, even if we need different values of t to do it. So, and this is something you might want to be careful about if you're doing examples in the textbook, is your answer, if you're looking at the solution in the back of the book, their solution might look different because they might have chosen a different point. Or maybe they did QP instead of PQ, and they got a vector going off in a different direction. So you just have to be a little bit careful looking in the back of the book and don't automatically assume you're wrong just because your answer looks different than their answer. And that's just a marking nightmare when we try and mark tests, but that's also not your problem. All right, so any questions about these ideas? All right, what if we just wanted the line segment from P to Q? So what if instead of going from P to Q and keep going, let me erase this so we can go back to the original. What if we wanted it to stop, to start at P and finish at Q? What would happen to our equation? Right, we'd put limits on the values of t. Absolutely would put limits on the values of t. So which value of t gives us the point P? So P is 1, 2, 3. Q is 4, negative 2, 1. Yeah. So P here happens at t equals 0. What about Q? What value of t is giving us Q? And it's a bit of a guess and check thing, although technically it's 3 equations you could solve. We need 1 plus 3t to equal to 4, 2 minus 4t to be equal to negative 2, and 3 minus 2t to be equal to 1. Yeah, that happens at t is equal to 1. So in other words, if we want all the values in between p and q but nothing else, somebody said limit the values of t. So what are we limiting them to? Yeah. So if we ever just wanted a line segment instead of the entire line, then the actual equation doesn't change. You just need to figure out the starting and the finishing value of t. For those of you who have or are taking Calculus 2, this is very closely related to the parametric equation stuff you would see in that course. Although that course does a little bit more extreme stuff with it than what we're seeing here. All right, so any questions about finding the equation of a line? Well, if we can do it for a line, why can't we do it for a plane? So see if we can find vector and parametric equations of this plane through a given point and parallel to multiple vectors. We would tack on the restriction at the end. The equation wouldn't change, so it would stay exactly as what we had before. We just add on the extra restriction. All right, so to find the equation here, now I am going to say we are talking about the vector and the parametric equations of this plane. We're not talking about the general form. We already saw back in the last section that there is a general form of the equation of a plane, and we are going to talk about that in section 3.5. But for here, we are just going to start with finding a very similar type of equation than what we would have had for lines. We want a similar type equation here. All right, so we want to come up with the same type of idea. Given some point Q, how do we write it in terms of P, U, and V? This is a little harder to see the geometry. Any ideas, though? No, we're not talking about normal vectors. We're not talking about normal vectors. We'll get to that in 3.5. We'll get to that in 3.5. Which is an alternative way of doing it, but there's benefits to both ways. So we're going to see both of them. Not sure what you mean by solve for Q in both vectors. Right, but that was a line. And PQ is neither, in general, is neither parallel to V nor is it parallel to U. We can't really use, at least immediately, we can't use our ideas from the last question because PQ is neither parallel to U or V. Any other ideas? I'm not saying that's wrong, but where on earth did that come from? I'm being educational now. I'm not seeing a single perpendicular here. So the idea is, and some people are getting at it, is all right, I want to get from P to Q. But the idea is I'm going to travel in one of two directions. We got these slanted streets that always go in these two directions. I'm going to travel in these two directions. So I need to travel either in the direction of U or travel in the direction of V. So I'm going to travel in the direction of U. I might go a little further than U. And then I'm going to travel in the direction of V. Try and keep it parallel. I think I went a bit too far. Let's backtrack. Missed my turnoff. And then I'm going to travel in the direction of V. And I'm going to get there. So I first travel in the direction of U, but I don't necessarily go the exact same length, just the same direction. And then I'm going to travel in the direction of V. We make ourselves a little parallelogram, except it's not exactly U plus V. Somebody suggested U plus V, and that's very close. But it's not exactly U because while we went in the same direction, so we're parallel to U, but we're not the same length as U. So it's a scalar multiple of U. Same idea here, that's a scalar multiple of V. So Q is going to be equal to P plus a scalar multiple of U plus a scalar multiple of V. So someone put the equation in the chat and it was the perfectly correct equation, although I might have mixed up the S and the T on the U and the V, but the choice of parameter doesn't matter. And we get our X, Y, and Z to be equal to P, 1, 2, 3, plus some parameter of U, plus a different parameter for T. So this would be our vector equation of the plane. The difference being is that we have two parameters instead of just having the one. Algebraically speaking, there's a lot of similarities there. The geometry is a little bit weirder. Right. The idea is we make this parallelogram, but we need to alter the lengths of the vectors by multiplying by that parameter, because all we have is parallel, we don't have the exact vector. All right, so any questions about those ideas? All right, so parametric. This was the vector. Parametric is the same x is equal to 1 plus 2s minus t, y is equal to 2 plus 3s plus 2t, and z is equal to 3 minus s plus 4t. So in terms of the parametric, we have one extra term, but the ideas are still the same. So this is how we can handle the equation of a plane. All right. Any questions about the ideas behind this before we see a few more examples? All right. I claim it makes sense that we have two parameters here. There's a very geometric reason why a line should have one parameter and a plane should have two. And we actually briefly discussed this in chapter 1 in a completely different context. But why does it make sense that a line had one parameter but a plane had two? Right, exactly. Exactly. A line is a one-dimensional thing. The line could be in 3 dimensions, but a line itself is a very one-dimensional thing. One dimension, one parameter. A plane is a two-dimensional thing. 2 dimensions, 2 parameters. So it makes sense that we're looking at 2 parameters here. One for each vector. All right. What if we had a 3-dimensional plane in like 4 space or something in A04? Hyperplane? If we had a hyperplane that was 3-dimensional, then yeah, it would need 3 parameters. Obviously, we lose a bit of the geometry when we do that, but algebraically speaking, it still makes sense. All right, how could this go wrong? Big note. Big note. Actually, that's not big enough. Big note. How could this go wrong? I still want to be able to have space to write things. What could go wrong with the geometry here? So let me go back to the picture. Actually, let me just draw a new picture. So we had U, and we had V. We wanted to get any other point on this plane using U and V and creating this parallelogram. And it was weird and geometrically fun, and we could shift around and we could eventually get to Q. I claim something could go wrong if U and V aren't really nice. I can really use this in my other class because this happened in when we did one of the earlier examples. Or was it this class on Tuesday? It was this class on Tuesday where something went wrong and I said, oh, let's find a different point. Yeah, if U and V are parallel. If U and V are parallel, this doesn't work. If U and V are parallel, all the linear combinations we get are still just going to be along that line. We're not going to get to Q if U and V are parallel. So U and V can't be parallel. If U and V are parallel, this really is just making the equation of a line in a more convoluted way. So in order to use these ideas and the other ideas we'll see in section 3.5 from a different perspective, we need 2 vectors parallel to the plane that aren't parallel to each other. So we'll see that coming up. If U and V can be perpendicular, that would be perfectly fine. The only thing that can go wrong is if they're parallel, or, I mean, the 0 vector never works well with anything, but opposite direction is still parallel. Opposite direction is still parallel. How would we get there? I'd still travel along U. Oops. I travel along U to here, and then travel in the direction of V here. Yeah. Opposite direction still qualifies under parallel. Then the scalar multiple would be negative. So if V was going, let's say, off in this direction, then we'd have, negative V, and we'd do it that way. Yeah, so nothing about these these parameters say they have to be positive, because we always have to have the option of going in the opposite direction depending on what's going on. All right, anyway, keep the questions coming. This is great. See if we can figure out the answer to this one. What kind of equation? Like the question that'll come right after this question? Like find the vector and parametric equations of that plane? If that's the question, stay tuned for right after this one. Yeah, we're going to see an almost exact thing like that with different numbers will be our next example. Granted, think about section 1.1, and we basically answered that question in section 1.1. 3 points don't make a pair. Well, 3 points kind of do. I mean, technically, we don't need that answer to this. But 3 non-collinear points, by that I mean 3 points that aren't in the same line, they kind of do make a parallelogram. Well, you know what? That's not true. That's not true. 3 points make 3 parallelograms. But the point is, all 3 of those parallelograms would be on the same plane, which is kind of the idea here. Because if you had 3 points, then, a parallelogram would say you'd have to finish this off. But then again, you could do this. The vector, no. The plane will. We can make 3 different parallelograms there. But no vector is going to pass through all of them. The plane is going to be what passes through all of them. I have a big problem with your use of the word the. Yeah, it's not just one vector. Right. So, if we need to find the equation of a plane, what are the things we need based off what we just did in the last question? We need a point and not a vector. We need 2 non-parallel vectors. So we need a point, in which case we have 3 of them here. Take your pick. So we need a point, and we need 2 vectors that are parallel to the plane, but not parallel to each other. And unless P, Q, and R are all on the same line, in which case this question doesn't even make a plane, least not one specific plane, we can get any point we want, and our two vectors are going to be, let's say, PR and PQ. So for example, U would be equal to 0, -4, -2. V is equal to 1, 1, 1. And now we get, again, does it matter which point we use? No, we could use any of the 3 points. I chose P because alphabet, but you choose whichever point you'd like. And we can get our vector equation of the plane. And again, parametric. X is 1, I guess, plus t. It's 0s. Y is 2 minus 4s plus t. And similar thing with the z. So again, the whole game is, given the information in the question, can we find a point, and can we find two vectors that aren't parallel to each other? How do we know these two vectors aren't parallel to each other? Right. They're not multiples of each other. Two vectors are parallel. I mean, zero vectors mess things up, but two vectors are non-zero vectors are parallel if and only if they're scalar multiples of each other. And it shouldn't take you too long to realize these vectors are not actually multiples of each other. There we go. Any questions about this? All right, did I have to make U and V the way we did? That's usually the question I get asked, so I'll ask it. No. I could have let U be equal to RQ and V be equal to QP if I wanted to. That would have been fine. I could have been, QP and RP if we wanted to. If we wanted to, we could have even had PQ or PR and RP. Or could we actually do that last one? No. Why can't we do PR and RP? Other than then why have Q at all? Yeah, they'd be parallel to each other. So the idea is you could choose whichever vectors you like, except you can't really choose them to just be the same vector in the opposite direction. But yeah, if you wanted to do RQ and RP, that would be perfectly fine, unless they happen to be on the same line, in which case we got bigger problems. Can you have more than 3 points? Good question, and I'm going to answer that while talking a little bit here. So this is kind of the question that was popped in the chat. Determine vector and parametric equations of this plane right here. What are the criteria for vector equations of a line again? You would need a point on the line and a vector parallel to that line when we did the vector equation of the line. The difference with a plane is we need two vectors, not just one. Can you have more than 3 points? Sometimes, but it's tricky. If let's say we had the equation of a plane, so 3 points will give us the equation, or 3 points that aren't on the same line will give us the equation of a plane. If we had more than 3 points, something could go wrong. What could go wrong if we had more than 3 points? Yeah, it's possible the first 3 gives you a plane, but the fourth one isn't on the same plane. So when you have more than 3 points, it's possible there is no plane that passes through all of them. Now, there might be, but the only way to know is to find the equation. I shouldn't say the only way to know. The only way we can probably think of right now is to find the equation that passes through 3 of them and then just check whether the fourth one is actually still on the same plane. Otherwise, the answer is there is no plane. In the same way, 2 points determine a line. So if you have 3 points, it might be a line that goes through all 3, but there's no guarantee. All right, so back to section 3.1 or section 1.1. How do we find the vector equation of the plane passing, or because this is the equation of a plane. X plus 2y plus 3z equals 4. We've just been talking about that in our last section, that's the equation of a plane. If it's the equation of a plane, it should have vector and parametric equations. So what are they? There's 2 free variables. Y equals s, z equals t, and then x is equal to 4 minus 2s minus 3t, and we're done. Well, that's the parametric. That's it. So that would be technically, I guess, 400 plus s times 1, or sorry, negative 2. We're kind of doing, we did all of our other ones where we found the vector and then did the parametric. Technically, we're just reversing that process. But yeah. Great question. How do we know it's a free variable? Well, let's turn it into a matrix. 1, 2, 3, augmented with 4. We got our leading one. So the fact that we had our plane in this linear equation form really just means a question like this is just a weird looking, sure, it's just a weird looking system of equations. It's just a weird looking system of equations, which means stuff we did in chapter 1 solves it for us. It's in reduced row echelon form. There's no parameter, or there's no leading one in columns 2 and 3. So we get parameters there. It really is just a chapter 1 question. All right, I'll stick around and answer more questions. If anyone has any questions, please do stick around and let me know. If not, that's it for today. I guess I'll see you in 12 days.